To predict the products of these reactions, I brought in this diagram from our lesson to show you how to use it most effectively. And you can also add to it, whatever you need. The primary thing you need to be able to do is to determine what is the order of your alkyl halide, or what is the order of the carbon that attaches to the heteroatom. So right here on this first molecule, we have a tertiary carbon that has a chlorine. So because we have a tertiary carbon, I'm going to be looking in this column, my tertiary column. Now I need to identify what I'm reacting with. So I have water. Water is a weak nucleophile. It is also a weak base. So where those two things match, I have an SN1 and E1 mixture of products. So to draw the SN1 and the E1 mixture of products, I would have my OH. Don't forget your methyl, so that's my substitution. We weren't given any stereochemistry because this is not a stereocenter. And then for the E1 products, I'm going to form this as my product. Now for B, again, we have our tertiary alkyl halide, and now we have sodium bromide. Well, sodium bromide, NaBr, remember 9 times out of 10 when you see a metal in this class, you will be delivering an anion. So imagine that we have bromide. I'm not sure why I can't quite see my pen today, but we will have bromide. So with bromide, we have a good nucleophile, but a weak base. So we're tertiary, we have a strong weak, we will form no reaction. There's no product to predict. There's not going to be a reaction. For the next one, with our product being C, again, we have our tertiary RX, our tertiary alkyl halide, and now we have sodium hydroxide. Sodium hydroxide is both a strong nucleophile and a strong base. So we will form the E2 product, and the E2 product looks an awful lot like the E1 product. So our elimination product is made. Now, if I'm going to try this instead. So for E, we again have that tertiary alkyl halide, but now we have potassium T-butoxide. Now that is a strong base, but a weak nucleophile. So I'm looking in this row, and it's tertiary. So I'm going to form an E2 product. The E2 product, as we found out above, looks like this. Although that is terribly messy, that's approximately what it looks like. Oh my goodness. Like that. For F, here we have a benzylic bromide. Now, fundamentally, that is primary. And we have this weak nucleophile, weak base. So we're primary, weak, that would be no reaction. But because it's benzylic, we have some extra stability. So we actually do form a substitution reaction here. This isn't something that would be asked in my class, but if you're studying for the MCAT or something similar, I have no idea if you're going to need this information. So when you have a benzylic alkyl halide, you have some special stability. So you will form the substitution reaction. For G, again, it's primary, it's benzylic. We have a strong nucleophile and a strong base. Okay, so we have strong, we're primary, we're going to form the SN2 reaction. For H, we have a weak nucleophile but a strong base. We're still primary and benzylic. We're going to form the E2 product. Now, in order to form the E2 product, though, we have to have a beta hydrogen. We do not have a beta hydrogen, therefore, there is no reaction here. For the next one on my list is actually L. And here I have a secondary carbon that is attached to my heteroatom. So I'm going to be looking in this column, my secondary column. Now I have water. Water is a weak nucleophile, weak base. That means we're going to form the SN1 and the E1 products. So the SN1 products, we're going to form a mixture. So I'm going to draw it flat, a mixture of both enantiomers with of an alcohol. So we have this hydroxy group. We're also going to form this elimination product. Now, because the carbocation would be here, it is possible for it to migrate. And it is a carbocation, so it's possible to form this as our product as well. When I ask you a question similar to this on the test, I need you to tell me both enantiomers are formed. I need you to name both enantiomers. Now, to the next column for product M up here, we have a primary alkyl halide. So we're going to be looking in this column here, primary alkyl halide, and we have sodium bromide. Remember, sodium bromide, when you see a metal and sodium is a metal, it is delivering an anion. Bromine is a strong nucleophile but a weak base. So we expect an SN2 reaction mechanism to occur. So the substitution product would look like this. For N, we have a primary alkyl halide again, and this time we have T-butyl lithium. Again, we have lithium and our T-butyl group. The lithium is delivering the T-butyl anion. So that T-butyl anion would then be a weak nucleophile, but a strong base. So I'm looking in this column here, and we would have an E2 reaction mechanism expected. So that product, we need to look towards our beta hydrogen. This is alpha, this is beta. We take away our beta hydrogen and make a new double bond between alpha and beta. For O, we also have a secondary carbon here. That secondary carbon is going to be attacked somehow by our sodium hydroxide and DMSO. Now, sodium hydroxide is one of those strong strongs, and because we are given that solvent, we need to pay extra close attention. Because although it is a strong nucleophile, what happens in DMSO? Well, DMSO is an aprotic solvent. Remember, an aprotic solvent will enhance nucleophilicity. It will dampen basicity. So, because we dampen basicity, we're actually looking at a strong nucleophile, weak base scenario with this is secondary alkyl halide. So we're looking at an SN2 reaction here. And because it is SN2 and you are given, well, this is supposed to be a wedge, it's difficult to do, but we need to flip the stereochemistry so that the OH is in the rear on a dash. For P, this time we have the same secondary alkyl halide, and now we have potassium T-butoxide. Again, the potassium is simply delivering the anion. This is a charged anion, and it is a strong base, but a weak nucleophile. So because of that, and we are in a secondary, and we have a secondary alkyl halide, then we form the E2, we take the E2 mechanism, and we form the E2 product. And this will fall towards the beta carbon that is most substituted. So we will go towards the extramethyl group. Now for Q, we have a tertiary carbon that is attached to a heteroatom. So this guy is tertiary. And NBR, again, NBR is a strong nucleophile but a weak base. So we expect there to be no reaction for Q. For R, we have, again, the tertiary carbon with the heteroatom, and then we have sodium hydroxide. Well, sodium hydroxide is a strong nucleophile, but also a strong base. We aren't told what solvent we're in. We're kind of left to our own devices here. So what are we going to do? Well, it's going to be E2. And it's going to be E2 because if it was a strong nucleophile, because it is strong, and regardless of what solvent it is, when you have a tertiary alkyl halide, it's E2. So our E2 reaction mechanism produces a product that puts a new double bond between the alpha carbon and the beta carbon that has the most substitution. For S, here we're given a ring structure, and the bromine is on a secondary carbon. So we're looking at this column. We're given this methoxide. Remember, methoxide, we have sodium here, so we're delivering the anion. It is charged. It is a strong nucleophile. It is a strong base. We are in DMSO. DMSO is aprotic. So aprotic means that although we have a strong nucleophile and a strong base, we are dampening that basicity so that we only form the substitution product. And because we're going SN2, when you draw this, you need to draw it with the methoxide up here in the equatorial position above the ring. And of course, the bromine comes off. For T, again, we have the same nucleophile, but this time we're in methanol. So although we have this strong nucleophile, strong base, as soon as it hits that methanol, it gets surrounded by a cage of methanol. And when that happens, we dampen the nucleophilicity and we increase the basicity. So when we increase the basicity, what we're going to do is remove the bromine and put a double bond between the alpha and the beta carbon. The alpha and the beta carbon is the alpha carbon is the one that has the heteroatom, and the beta carbon is next door. So we would go this way. For U, we have potassium T-butoxide. T-butoxide is a strong base and a weak nucleophile. We have a secondary alkyl halide here, so we will form the E2 mechanism for U. And that looks just like what I drew up here. It's the same mechanism, or it is the same mechanism in the same product. And for V this time it is a secondary alkyl halide, but it is an allylic alkyl halide. So that adds a little bit more stability, but it is still secondary. Now look at the nucleophile. We have sodium iodide. Remember that sodium is delivering an anion, so iodide is charged. This is a strong nucleophile. It is a weak base. Because it is a strong nucleophile and a weak base, and we have a secondary alkyl halide, we're going to form the SN2 product. So the SN2 product would look like this. Remember to flip your stereochemistry if you have an asymmetric center. And for W, we have this same secondary allylic alkyl halide. This time we have sodium hydroxide, and our sodium hydroxide is in methanol. Sodium hydroxide is a strong nucleophile and a strong base. As soon as we add the solvent, the methanol builds a cage around those hydroxide anions. And because it builds that cage, it dampens down the nucleophilicity and enhances the basicity. So we are looking at a weak nucleophile, but a strong base as soon as it hits that solvent. So we will draw the E2 mechanism. And this time, what we'll end up doing is conjugating. So these electrons, although the bromine does leave, it leaves after this hydrogen is removed and the electrons fall here. And we make this conjugated system, which is a special stability state that we will talk about in organic 2.